Hello, everyone. Good afternoon, good evening, or good morning. Anything. I hope it's not good morning to anyone. It is too early. So I'm at Cisco Research. I'm head of cybersecurity research based out of San Jose, California. I'll be talking about post-quantum security and 5G challenges and issues. This talk, I have what, 15 minutes, Ryan?
Yes.
Okay. If you could give me a nudge around, 2-3 minutes or 5 minutes remaining, that will be helpful.
Okay,
Thank you.
will do.
Thank you. So, in order to dive into what the challenges that quantum threats pose or quantum community poses for 5G, like to take a use case, specific use case, right? Look at space communication security. The LEO satellites, satellite communication, with the growth in space industry, space communication security is becoming extremely important. If you look at NASA space communication security requirements, right? They say that the communications to and between spacecraft must be extremely secure and reliable. Okay. However, the security of the communication between spacecraft and ground stations and maybe other satellites are many times secure with communication protocols or cryptography protocols that are not resistant to quantum threats. Okay, so for example, IPsec, right? So IPsec is many times is used for that purpose. Now imagine, just to give an example here, I'm just noting SpaceX, but I don't mean to point at SpaceX, but I'm just in general talking about any space communication. We have reusable rockets now. The rocket puts a payload onto the orbit, then returns back to Earth. Now, any communication that is happening with the ground station, right, or ground stations can be intercepted by rogue state or entities. They can break the communication using quantum threats or quantum computing systems, right? And then command and capture the re-entering rocket, and then reroute it. They can actually reroute it as a missile to a military or civilian area or elsewhere, right? So the use case tells us, the scenario tells us that quantum computing is shaping up a great future for all of us, for the entire industry and the world. However, if we do not take care of the quantum threats for 5G or existing communication and computing world with respect to public key crypto and other cryptographic protocols, then we're actually going to be in grave danger. So given that, right, now the question is the space agencies are trying to use 5G? Yes. You look at this ESA, European Space Association's space agencies slide. That talk about how to use 5G and 6G going forward. Of course, 5G, 6G are going to be, we've talked about that, how many other speakers have looked at them as well, right? But here we are essentially looking at how the communication should be protected. Look at how Lockheed Martin in US is talking to Omnispace on the 5G network, right? On building a global 5G network. Now, let's try to find out what are the overall landscape that looks like for 5G applications, right? You look at smart city, we looked at space, smart cities, self-driving cars, augmented reality or XR, virtual reality, mixed reality, whatnot, and of course, cloud computing, where you can send gigabytes in seconds, gaming, but so important point here is that as we are rolling out 5G, there are several applications we are aware of, and in that relationship, we should be able to find out what are the threats. Now let's switch the gear from the scenario. We talked about the specific use case, how quantum threats to 5G can influence a kind of as a real cyber physical threat. Now let's switch gear to quantum computing, right? Quantum computing has been progressing for a long time, but over the last decade or so, it has actually gained momentum, especially when IBM research back in early 2010s brought the quantum experience to online on the cloud, and of course Google announces Quantum AI Lab, and then right now we're moving towards Google announced quantum supremacy in 2019. IBM has come up with about a significant amount of quantum volume with about 127 qubits with a regular architecture, and then they are going into Osprey to 433 qubits, and by 2023 they'll have 1121 qubits. Right? But what they talk about is quantum volume is more important than number of qubits. Okay, that's a measure of quantum computing power. The question you might say that, hey, we're not there yet to be able to even break RSA cryptography, right? Or like maybe even 512-bit keys, right? Why are we worried about it right now? Okay, but we are actually progressing in a nonlinear fashion to achieve the amount of quantum computing power that is needed to break them. But that is needed for real-time attacks on communication channels or other channels, right? Or even data security, right? However, imagine the systems that are now the 5G equipments, right? That they are that are being built that will stay for decades, right? At least 10 years into the timeline, right? They will be using let's say TPMs, okay, for their root of trust. They would be implementing public key cryptography, and they can be broken. Then those devices can be swapped out, and there will be for malicious devices, okay, or the encrypted data from 5G communication channels can be harvested and kept for decryption later on, by rogue entities, and decryption can be carried out by breaking the cryptographic system that has been used, right? A cryptographic protocol that has been used to encrypt them. So I look at the timeline. This is kind of a 2020 plot, right? It seems that by 2026 we'll have a number of qubits, and as I said, it's a nonlinear progress curve that we have. So within next 5 to 7 to 5 years, right? We'll have enough number of qubits or quantum computing power to actually break RSA. So given that, right, and if you look at here, right, about this is essentially if you look at the timeline, right, that there's a about 2022 NIST is talking about post-quantum cryptography, right? These are the there's the third round that is ongoing, and that would standardize the lattice-based cryptography protocols and other protocols that would be used for encryption, digital signatures, and other cryptography protocols, right? And then if we wait till then it will be too late. That's the bottom line, right? So So by 2026, it says that about PQC, post-quantum cryptography compliant hardware manufacture would be carried out around this time frame, okay, 2026. Okay, because the next official PQC standard will be published. But before that, we have to actually talk about how to standardize even the security architecture of 5G. Right? And by this time frame, about 2030, let's say about 22.7% quantum computer experts consider the 2048-bit keys encryption of RSA can be attacked. Okay, but that's not too far out. I think, in my opinion, there could be an early attack. The way quantum computing is progressing. Right. So, given that scenario, right, how many bits or qubits are needed, right? Look at essentially what the two types of algorithm. One is about source algorithm that is used to break public key crypto, like RSA and discrete logarithmic problems for elliptic curve, right? But lattice-based cryptography, to a great extent, have been shown to be resistant, and that is where next post-quantum cryptography standardization is going to lay their foundation and base in. So if you look at essentially our and then of course Grover's algorithm is about reducing the key space search for for any classical algorithm, especially AES. Then you have to increase the size of the keys and carry out other measures. Right? So RSA, look at the number of qubits in need, logical qubits in need actually is for about 1024, you need about 2050, and for 2048, you need 4098 logical qubits. Okay. And that would be carried out in 28 hours.
2 minutes, Ashish.
Okay, thank you. Yeah. So if you look at the one example of the cryptographic protocol and architecture that is provided in the security architecture and procedures for a 5G system document, right? That they are using elliptic curve systems, and that needs to be changed. Of course, they have mentioned in their document, in their report, that that quantum resistant algorithms need to be supported, right? So we need to move towards that soon enough. If you look at Google's architecture, right? For how cloud can be used for the virtualized network functions and software-defined architecture for 5G. Right? This is that there's a different kind of capabilities available hardware, and then there are data center like edge data center. Then there are breakout edge data center and core data center, right? And in that space, right, what are the quantum threats on the device side? Whatever the device, like all the players like Qualcomm or even other players, right? They need to take a look at that. I hope they are taking a look at that now. And then RAN unsafe crypto would be there, and quantum unsafe cryptography implementation usage on the across the spectrum of cloud computing for 5G. Now, this is a security innovation with Cisco from Cisco. From Cisco, we have a white paper in 2018, and we talked about. Of course, I was not part of the white paper. I'm just mentioning that I just joined last year Cisco research. So the if you look at that, right, then we have about several layers where we have to bring in quantum safe cryptography into place at the device level, where device tampering, firmware protection, or firmware attacks have to be addressed, because firmware would be using public key crypto or maybe AES. So we need to provide some form of key agility there. Then of course there are RAN specific threats on encrypting the channel, authentication, device authentication, user authentication, etc. Right, and then across this spectrum here that quantum answer cryptography is being used, and we should try to minimize that or try to find out how to minimize the attack surface, the threat surface. So there is work going on at Cisco Research and across Cisco on making this secure. We're not yet there from publishing the details, but we are working on how to develop a way to minimize attack surface and increase quantum safety compliance and quantum safety readiness. Thank you.